in this session, let us solve some problems related to uniform plane waves traveling in arbitrary direction in a medium, and also the problems related to the polarization of an electromagnetic wave. We will also solve a problem related to the dielectric boundaries and so on. So, let us consider a problem here that the complex vector electric and magnetic fields in a dielectric medium are given by this. So, E is equal to minus j root 3 unit vector x plus 2 unit vector y plus j unit vector z with a phase function which is e to the power minus j 0.02 pi x plus root 3 z, and the magnetic field is given as 1 upon 30 pi root 3 x plus j 2 y minus z cap with a phase function which is same as this, which is e to the power minus j 0.02 pi x plus root 3 z. And what is asked is, show that these fields represent fields of a uniform plane wave. Also, we have to find the frequency and the velocity of the wave. Also find the phase velocities along the x and y direction and z directions. Also find the state of polarization of this wave. So, first you have to show that these fields represent a uniform plane wave. So, we know from the property of uniform plane wave that the direction of wave propagation, the electric field and the magnetic field, they are perpendicular to each other, and also at every instant of time the ratio of the magnitude of electric field and the magnitude of the magnetic field is equal to the intrinsic impedance of the medium. So, essentially these are the properties we are going to use to establish the uniform plane wave nature for these fields. So, essentially we have to show that E is perpendicular to H and is also perpendicular to the direction of the wave, which we denote by the unit vector n. Now, we know that if you write down the fields in the standard form, that any electric field is having some amplitude E0 with a phase function which is e to the power minus j beta into n dot r, and then we can compare this phase function with the phase function which is given for these fields. So, this phase function. So, essentially we can get from here that this quantity n dot r is n dot r is equal to, as we know, is cosine of phi x into x plus cosine of phi y into y plus cosine of phi z into z. And in this case it is given this quantity here, which is x plus root 3 z. So, first of all we can take this quantity for which and compare with this. So, that essentially gives you this quantity as x plus root 3 z, and as we know this quantity should have, the n should have a magnitude which is unity. So, if you can write down this quantity appropriately, we can take this as 2 times x 1 upon 2 into x plus root 3 upon 2 into z. So, that is the quantity essentially which represents the n dot r. So, because this quantity here corresponds to cos of phi x. So, what that means is, from here if I compare these two, we get phi x is equal to 60 degrees, phi x equal to half. So, that is equal to pi by 3. We get phi y, there is no term for y here, that means this cos of phi y should be 0. So, phi y is equal to pi by 2, and then phi z, which is the angle which the wave vector makes with the z axis, that is equal to cos of phi z is root 3 by 2. So, that is equal to 30 degrees, which is equal to pi by 6. So, one thing we can note from here, that since the phase function has only x and z terms in this, essentially the wave is propagating in the xz plane, and that is what essentially we see here, that the wave normal makes an angle 60 degrees with the x axis, 30 degrees with the z axis, and 90 degrees with the y axis. That means the vector lies in the xz plane. So, essentially the wave is travelling, if we write down the coordinate axis, this is the x, this is y, this is z. The wave essentially is travelling in this xz plane. So, it is travelling something like that. This is your unit vector n, where this angle is 60 degrees, this angle is 30 degrees, and this angle with y, that is 90 degrees. So, from here essentially we get the unit vector n as we got, that is 1 upon 2 x cap plus root 3 upon 2 z cap. Now, we have to show that the electric and magnetic fields are perpendicular to each other, and they are also perpendicular to the direction of the wave vector, which is n cap. So, for this we can take the dot product of E h and E and the unit vector. So, we get E dot h, that is equal to, if I take from here, we will get the dot product of these. So, this will become minus j into 3. So, that gives me minus j into 3 plus 4 into j plus 4 into j minus j. So, that is equal to 0. So, that means the electric field for this is perpendicular to the magnetic field. Same thing we can do for the unit vector and the electric field. So, you take electric field and the dot product of that with the unit vector, that is equal to minus j root 3 x plus 2 y plus j z dot unit vector n, which is 1 upon 2 x cap plus root 3 upon 2 z cap. So, that is equal to minus j root 3 upon 2 minus j root 3 upon 2 plus j root 3 upon 2, that is equal to 0. So, now we have got E is perpendicular to H, E is also perpendicular to N, that means E, H and N are perpendicular to each other. That is one of the property of uniform plane waves. So, it satisfies this property, and therefore, we say that the fields represent the uniform plane wave. Now, to find out the frequency and the velocity of the wave, essentially we have to find out the propagation constant beta, and for that again we take this term, which is the phase term, this quantity here, and we do some rearrangement so that we can get this quantity propagation constant beta. So, the phase function which is given there, which is e to the power minus j beta into n dot r. If I take this quantity now, from here I will get beta into n cap, that will be equal to 0.02 pi, this phase function here, into x cap plus root 3 into z cap. Writing this as unit vector, this will be 0.02 pi into 2, and this will be 1 upon 2 x cap plus root 3 upon 2 z cap. So, you multiply by 2 and divide by 2. So, this becomes unit vector. So, this quantity then essentially represent the phase constant beta. So, from here we get this phase constant beta, which is equal to 0.04 pi radians per meter. Now, to find out the dielectric constant, for the finding out the velocity, essentially we have to find out the medium properties. Still we do not know, because we have the frequency is not given. In fact, we have to find the frequency of this wave. So, first we have to find out what is the medium property or what is the velocity of the wave, and that we can find out essentially from the property of uniform plane wave, that is the ratio of mod E to mod H, that should be equal to the intrinsic impedance of the medium. And since we are talking about a dielectric medium, the permeability of the medium is same as the free space permeability, only the permittivity of the medium is different. So, we know that mod E upon mod H, that should be equal to the intrinsic impedance of the medium, which is square root of mu upon epsilon, and since the medium is only dielectric, this is equal to mu 0 upon epsilon 0 into epsilon r. Now, to find out the ratio of this magnitude, since the electric and magnetic fields are having this component which are J, so essentially it means that the fields are complex. So, what we can do is we can find out the magnitude of electric and magnetic field at some instant of time, and since we know that the ratio of electric and magnetic field should be equal to intrinsic impedance at every instant of time, the ratio can be taken at some instant of time. And the easier way to do that is take the time t equal to 0. So, what these components are showing you, that these two components are 90 degree out of phase in time with respect to the y component. So, if I take t equal to 0, essentially these two components will be 0 at that instant of time, because they are 90 degrees out of phase. And at the same instant of time, if I take the magnetic field, this component will be 0, this will be 90 degree out of phase. So, at t equal to 0, if I take the electric and magnetic fields, that will be corresponding to this term for electric field and these two terms for the magnetic field. So, if I take at t equal to 0 some time, then the magnitude, the electric field for this is given as 2 into y cap, with of course multiplied by the phase function, and the magnetic field at that instant of time will be 1 upon 30 pi into root 3x minus z cap. So, at that instant of time, now we can find out the magnitude of electric and magnetic fields. So, this gives me that the magnitude of electric field mod of E, that is equal to 2, it is oriented in y direction, and mod of H will be mod of this. So, that will be equal to 1 upon 30 pi into square root of 3 plus 1. So, that will be mod of h from here, mod h will be equal to 2 upon 30 pi. Then we can take the ratio of these two, and from there we can find out the dielectric constant of the medium. So, from here essentially we get mod E upon mod H, that is equal to 2 upon 30 pi, that is equal to 30 pi, that is equal to square root of mu 0 upon epsilon 0 into 1 upon square root epsilon r. We just take here the square root of epsilon r out. So, we have this quantity which is square root of mu 0 upon epsilon 0, which is nothing but the intrinsic impedance of the free space, and that number we know is equal to 120 pi. So, this quantity square root of mu 0 upon epsilon 0 is 120 pi. So, from here we can get square root of epsilon r, that is equal to 1 upon 30 pi into this is which is 120 pi. So, we get 120 pi, that is equal to 4. So, the square root of the dielectric constant, which we also call as the refractive index of the medium, that is equal to 4, and therefore, the dielectric constant epsilon r for this medium will be equal to 16. Once we get the dielectric constant, then we can find out the velocity of this wave in this medium, and that is the velocity of the wave v will be equal to 1 upon square root mu 0 epsilon 0 epsilon r, so equal to 1 upon square root mu 0 epsilon 0 square root epsilon r, and 1 upon mu 0 square root mu 0 epsilon 0 is nothing but the velocity of light in the free space, which is 3 into 10 to the power 8 meters per second. So, we can substitute here 3 into 10 to the power 8 meters per second for this, and square root of epsilon r is 4. So, the velocity will be 3 into 10 to the power 8 divided by 4 is equal to 0.75 into 10 to the power 8 meters per second. So, for this wave the velocity in whatever dielectric is given, which is having a dielectric constant 16, the velocity will be 0.75 into 10 to the power 8 meters per second. Once we know the velocity, then now we can find out the frequency of the wave, because we know that the velocity for the wave is omega upon beta, or from here, since we want to find out the frequency, which is equal to 2 pi into frequency f divided by beta. So, the frequency from here will be equal to velocity into beta v into beta divided by 2 pi. So, we have found out this velocity, which is 0.75 10 to the power 8 meters per second. We also have found out the value of beta, which is 0.04 pi radians per meter. We can substitute this. So, this is equal to 0.75 into 10 to the power 8 multiplied by beta, which is 0.04 pi divided by 2 pi. that if you simplify, that will turn out to be 1.5 megahertz. So, the frequency of this wave is 1.5 megahertz. The next thing we have to find out is the velocity of the wave in along different directions. So, we are supposed to find out the phase velocities along x, y and z directions. So, as we know that the velocity Vx, the phase velocity along x direction, is equal to V divided by cos of phi x. The velocity along y direction is V divided by cos of phi y, and the velocity along z direction is V divided by cos of phi z. And we have calculated this phi x, phi y and phi z. The phi x is 60 degrees, phi y is pi by 2, 90 degrees, and phi z is 30 degrees. So, from here we get the velocity along x direction, that is 0.75 into 10 to the power 8 divided by cos of phi x, which is 1 upon 2. So, you get 1 upon 2. So, that will be equal to 1.5 into 10 to the power 8 meters per second. The phi y is 90 degrees. So, cos of phi y is 0. So, the phase velocity along y direction is infinity, and phase velocity along z direction will be 0.75 into 10 to the power 8 divided by cos of phi z, which is cos of 30 degrees, which is root 3 by 2. So, this will be root 3 by 2. So, that is equal to 0.866 into 10 to the power 8 meters per second. So, since the wave is travelling in the xz plane, the phase velocity in the y direction is infinity, and these are the phase velocities which are in the two directions x and z. Now, to find the state of polarization of this wave, one way is to find out the equation of the ellipse which the electric field vector draws. But in this case, what we can do is we can look at the electric field and find out the magnitude of the electric field at different times. So, let us say if I write down the electric fields in this, electric field has three components. The x component is given by this, the y component is given by this, and the z component is given by that. So, here the magnitude is root 3 and there is a minus j, that means this x component can be written as E of x, can be written as root 3 cos of omega t minus pi by 2, that corresponds to minus j. The y component has an amplitude 2 and it has a 0 phase. So, we can write down the y component E y, that is equal to 2 cos of omega t, and the z component E z, that is equal to the j. So, it has magnitude 1 and phase plus pi by 2. So, that is cos of omega t plus pi by 2. So, this gives us root 3 sine of omega t, and this will give us minus sine of omega t. Now, we can calculate the field magnitude at different instant of time. So, let us consider the time which is t equal to 0. t equal to quarter period t by 4, t equal to t by 2, t equal to 3t by 4 and so on, and find out what is the magnitude of the electric field. So, at t equal to 0, if I take, then this field will be 0, this field will be 2, and this will be again 0. So, you will have E x equal to 0, E y is equal to 2, and E z is equal to 0, giving mod of E equal to 2. If I go after quarter period, which is t by 4, then this quantity will be plus 1, this will be minus 1, and this quantity will be 0. So, in this case you will get E x which is equal to root 3, E y is equal to 0, and E z is equal to minus 1. That again gives the mod of E, which is square root of E x square plus E z square, that will be equal to 2. Similarly, if I go one more time, which is t by 2, so again this will be equal to pi, you will get the magnitude which will be same. So, let us take a time which is not multiples of pi by 2, but let us say take a time which is t by 8. If I substitute for this now, this angle will be equal to 45 degrees. So, you get root 3 upon root 2. So, for this time you get E x is equal to root 3 upon root 2, E y will be equal to 2 upon root 2, 2 upon root 2, and E z will be equal to minus 1 upon root 2. Again, if we calculate the magnitude of the electric field, that will be equal to 2. So, what that indicates is, as the time varies from 0 to t by 8 to t by 4, the magnitude of the electric field remains constant, which is equal to 2. That means this wave represents a circularly polarized wave. Now, to find the sense of rotation, essentially we can look at this diagram, and the wave is travelling essentially in this direction. So, if I consider at t equal to 0, the electric field is in the y direction. So, the electric field is along y direction, which is like that. That is what is given by this. If I go at a t by time little later, the E x is root 3, E y is 0, and E z is minus 1. So, initially the field, the electric field was like that, and after a time t by 4, the E x has become root 3 and the z component is negative. So, essentially the electric field vector has moved like that. So, since this quantity z is negative in this, so the point which has moved here, the electric field vector, it will be root 3 in this direction and minus 1 in the z direction. So, the point will come somewhere here, that is where the electric field would be. So, essentially the electric field has gone from here to here, something like that in this direction. Now, since the wave is moving this way, if I now look in the direction of the wave, the electric field vector is rotated like this from here to here. That means this wave essentially represents a left-handed rotation. So, we have the sense of rotation for this wave, which is the left-handed. So, this problem clearly demonstrates how, knowing the electric and magnetic fields, one can find out the various parameters regarding the medium, the velocity, the frequency, the state of polarization and so on. So, if we systematically proceed with the concepts which we have developed for uniform plane wave, then by knowing the fields we can essentially find out the various parameters of the medium as well as the properties of the electromagnetic wave. Let us take a second problem. Here we have a uniform plane wave having 10 watts per meter power density, is normally incident on a 5 centimeter thick dielectric sheet with epsilon r equal to 9. If the frequency of the wave is 1 gigahertz, find the power density of the wave transmitted through the sheet. So, essentially what we have here, we are having a medium which is having a finite thickness, and then we have to find out how much field is transmitted on the other side of the sheet, which is having a dielectric constant 9 and a thickness of 5 centimeters. So, this problem essentially can be solved as follows. We have a sheet which is like that, whose dielectric constant epsilon r is equal to 9. On this side you have dielectric constant epsilon r equal to 1, and on this side also you have epsilon r equal to 1. Now, the wave is incident from this side, is normally incident on the dielectric slab, which is having a power density of 10 watts per meter. So, the power density P is equal to 10 watts per meter square for this wave, and it is having a thickness of 5 centimeter. This problem essentially can be solved in many ways. One is, since this is a normal incidence, we can treat it like a one dimensional problem. So, we can treat it as if you are having a medium here which is having certain impedance. So, it is like a long transmission line. Then you are having another section here whose medium parameter is this. So, it has different characteristic impedance, and then in this side again you are having an infinite medium. So, you have another line which is having an impedance which corresponds to epsilon r equal to 1. So, one of the ways to solve this problem is by analogy with the transmission line, which says this is equivalent to a transmission line. Then there is another transmission line here, and then the same transmission line again which continues up to infinity. Now, the characteristic impedances of these lines would be the intrinsic impedances of this media. So, here we have the intrinsic impedance which will be eta, which will be same as eta 0, which is equal to 120 pi. Here again you will have impedance eta which will be eta 0, which will be 120 pi, and in this case you have an impedance eta which will be eta 0 divided by square root of epsilon r. So, you will have here eta which is equal to 120 pi divided by square root of 9. So, that is equal to 40 pi. So, now the wave is incident from this side. You have a section here which is having an impedance, characteristic impedance of 40 pi, and you have the length of this transmission line which is 5 centimeter. So, this is, since this lies in infinite now, it will see an impedance which is equal to characteristic impedance of this. So, I can find out. So, this is equivalent to, this section is equivalent to, you have a transmission line of 120 pi, then you have a transmission line which is 40 pi characteristic impedance, and this is now, this line is terminated in an impedance which is equal to 120 pi. So, one of the ways to solve this problem now is you have to find out what is the power transmitted through the sheet on the other side. So, essentially we want to find out what is the power density which is gone to this resistance, which is 120 pi. So, if you go by transmission line approach, essentially what we can do is we can find out what is the impedance which would be seen at this location, then how much power has been transferred to that impedance, that is the power which is finally will be delivered to this impedance. So, we can get the power, and from there we can find out the power which is transmitted to this medium. For this we have to find out now this length, which is 5 centimeter, which you have to find in terms of the wavelength, and now the wavelength depends upon the dielectric constant of the medium. So, here the velocity we can calculate, and from there we can calculate the wavelength of the wave in that medium. So, since the epsilon r is 9, the velocity of the wave in that medium on the sheet that is equal to the velocity in the air divided by the square root of epsilon r, which is root of 9. So, that is equal to 10 to the power 8 meters per second, and the frequency is given for this problem is 1 gigahertz. So, the f given for this wave is equal to 1 gigahertz, that is equal to 10 to the power 9 hertz. So, from here we can calculate the value of lambda, which is the velocity divided by frequency. So, that is equal to 10 to the power 8 divided by 10 to the power 9. So, that is equal to 0.1 meters, or that is equal to 10 centimeter. So, in this medium the wavelength lambda is 10 centimeter. That means this length here 5 centimeter essentially is the distance of lambda by 2. So, in this case the problem is become very simple, that now this distance is equal to lambda by 2. And the impedance which you see, the normalized impedance, is transformed here at the same value at a distance of lambda by 2. So, essentially we can calculate this impedance and transform this impedance on the other side. So, you can get essentially the impedance which is 120 pi, which is on the other side. Once you get that impedance which is transformed here, then you can find out what is the power which is delivered to this load, and from there then you can find out the power density which is gone to the second medium. That is one approach. The second approach is, which is more like a wave approach, and that is, consider now this medium and the wave is incident on this. So, let us say this boundary is boundary, this medium is 1, this medium is 2, and this medium is 3. So, we have now the two media interfaces, one is from 1 to 2, another one is from 2 to 3. So, the wave is incident on this boundary, it sees the reflection and part of the energy is transmitted from here. This energy travels all the way up to this boundary, then part of the energy is reflected from here, part gets transmitted. This energy then travels all the way up to this point, since it again sees the medium discontinuity, part of the energy is transmitted here and reflected here. This energy again reaches at this point, it gets reflected, part gets transmitted. this one reaches here, again part get reflected, part get transmitted. So, what we can find essentially that the net reflected wave will be sum of all these reflections, this first reflection plus this second reflection plus the third reflection. If we sum up all that together, that gives me the total reflected wave in this direction. Similarly, the transmitted wave would be this transmitted wave plus this plus this. So, if I sum up all those waves together, that essentially give us the total transmitted wave on the other side. So, now what we can do is we can essentially find out the reflections which are coming from here. So, we can write down the reflection coefficient for each of these boundaries and the transmission coefficient on each of the boundaries, and then find out the total summation, and from there essentially we can get the total reflection and the total transmission. Now, if I say that the reflection at ij boundary, so that means 1 2 boundary, if I take, that would be gamma 1 2. So, from here let us say reflection I write down at an interface which is given by ij, that is nothing but impedance of the medium j minus impedance of the medium I divided by impedance of the medium j plus impedance of the medium I, and from here essentially we get gamma ij is equal to minus of gamma ji. So, if the wave is going from here to here, the reflection coefficient is gamma 1 2. However, when the wave comes here, the reflection coefficient this would be gamma 2 1. So, this one is gamma 1 2, this will be gamma 2 1, this will be gamma 2 3, and so on. Similarly, the transmission coefficient we can get tau ij, that is equal to 2 times eta j divided by eta j plus eta I. So, this transmission coefficient here would correspond to eta 2 divided by eta 1 plus eta 2. This transmission coefficient would correspond to eta 3, 2 times eta 3 divided by eta 3 plus eta 2, and so on. So, now if I write down, and you are having this distance d, and the phase constant in this medium let us say is given by beta. So, you are having the phase change when the wave travels from here to here, which is equal to corresponding to beta d. So, this wave travels a distance which is beta d, phase beta d. When it comes here, it has traveled a distance which is 2 times beta d. So, now what we have here is the first reflection plus the second quantity here, which is 1 reflection here, 1 transmission, 1 reflection, and 1 transmission, which is this way. So, if I write down now the total reflected field which is going to come from here, that would correspond to your E reflected, that is equal to gamma 1 2 E incident plus tau 1 2 then gamma 2 3 and tau 2 1. So, you can write here tau 1 2 E I, gamma 2 3 tau 2 1 with a phase term now which is e to the power minus j 2 beta d. The next term would be whatever has come here, this will be tau 1 2 plus gamma 2 3 gamma 2 1 gamma 2 3 and tau 2 1. So, we can we can write that. So, that is equal to tau 1 2 E I gamma 2 3 gamma 2 1 gamma 2 3 tau 2 1 e to the power minus j 4 beta d plus and so on. So, essentially if you see if I take this quantity common, you will have now a geometric series for this. So, we can write down now the reflected wave E r, that is gamma 1 2 E I plus tau 1 2 gamma 2 3 tau 2 1 e to the power minus j beta d into 2 and summation of the geometric series which we get. So, this term will be multiplied by E I upon 1 minus gamma 1 2 gamma 2 3 e to the power minus j 2 beta d. So, if I know now the field which is incident on this wave, then I can find out what would be the net reflected wave, which will be essentially given by that. So, precisely same thing we can do for the transmitted wave also, which is going to this. So, this transmitted wave will be this transmitted plus this multiplied by this transmitted, then there will be 2 reflection and then this transmitted. If I sum up again all these fields, essentially we will get the transmitted wave also on the line similar to this, that will be equal to tau 1 2 tau 2 3 e to the power minus j beta d into E I divided by 1 minus gamma 2 1 gamma 2 3 e to the power minus j 2 beta d. So, I can substitute now this value for beta d or 2 beta d, and I can substitute the value for gamma 2 1 and gamma 2 3, and from here then I can find out what is the transmitted wave. So, the power density which will be transmitted will be proportional to the mod t square. So, I can find out this quantity and can get actually the power transferred. So, in this case, since the quantities which are given are, the situation is this, that this is equal to epsilon r is 1, this is epsilon r is 1 and this is epsilon r is 9. Essentially we have the eta 1 which is equal to eta 0, eta 2 is eta 0 upon square root of epsilon r which is 3, and eta 3 is equal to eta 0 again. So, from here we can get essentially these quantities, which is gamma 1 2 which is eta 0 by 3 minus eta 0 upon eta 0 by 3 plus eta 0. So, that is equal to 1 upon 3 minus 1 upon 1 upon 3 plus 1. So, that will be equal to minus 2 upon 4 is equal to minus 1 upon 2, and gamma 2 3 will be eta 0 minus eta 0 upon 3 minus eta 0 plus eta 0 upon 3. So, that will be equal to 2 upon 4 is equal to 1 upon 2.